This is the Linear Algebra Lectures video series. You can find more information about this video as well as a link to the written textbook in the description below. Stick around to the end of the video to learn more about this video series and the associated teaching and learning tools I've created for it. Lecture 25, the Invertible Matrix Theorem. Our objectives for this lecture are to understand the statement of the Invertible Matrix Theorem and to apply the Invertible Matrix Theorem to determine whether a given matrix is invertible. So we've been talking for the last few lectures about invertible matrices, and all of these ideas come together in the following theorem. The theorem says that if we have a square n by n matrix, then these 12 statements are all equivalent. And remember that equivalent here means that all 12 of these statements are true for a given matrix, or they're all false for any given matrix. So if any one of them is true, then they're all true, and if any one of them is false, then they all have to be false. So the first part of this video will talk about the proof of this theorem to understand why it's true, and then we'll shift focus to talk about how we can apply the theorem to understand whether a given matrix is invertible. A lot of the work to prove this theorem is already done. Because A is a square matrix, saying that the matrix has n pivot positions is the same as saying that it has a pivot in every row, and the same as saying that it has a pivot in every column. And that's also the same as saying that the reduced echelon form of this matrix is In. We've also talked about the spanning columns theorem, which connects statements B, C, G, H, and I here. And we also have the linearly independent columns theorem, which connects statements B, C, D, E, and F. In lecture 24, we talked about how a matrix is invertible if and only if its reduced echelon form is In. And we also talked about how a matrix is invertible if and only if its transpose is invertible, and that the inverse of the transpose is the transpose of the inverse. So the only thing that we're missing here are statements J and K to connect to why this matrix must be invertible. And those two statements connect to the one-sided inverse theorems that we talked about back in lecture 22. For statement J, A implies J because if A is invertible, then we just let the C matrix in that statement be A inverse, and so then C times A equals In. For J implies A, if we assume that we have a matrix C for which C times A is In, then that left side inverse theorem tells us that we have a pivot in every column, and that we've already proved that that means that A has to be invertible. Similarly, for A and K being equivalent, we use the right side inverse theorem. First, if A is invertible, then we let D be A inverse, and then AD is In. And for K implies A, if D exists, for which AD is In, then the right side inverse theorem tells us that A has to have a pivot in every row, and that means that A has to be invertible as before. So a few things to note about this theorem. When we're looking at a square matrix, we can use any of these 12 statements to determine whether the matrix is invertible. Row reducing the matrix is always an option, but there are often easier ways. And so even though we could row reduce a matrix to determine whether it's invertible, in the rest of this lecture, we're going to focus on using some alternative methods to determine whether that matrix is invertible. The other thing to keep in mind is that this theorem only applies to square matrices. If we want to analyze matrices that are not square, then instead we should look at more general theorems like the spanning columns theorem and linearly independent columns theorem, because those theorems apply to matrices of any shape. All right, so now let's practice using the invertible matrix theorem to determine whether a given matrix is invertible. And again, keep in mind that we are intentionally avoiding just using row reduction here because we want to try to see how the other statements of the invertible matrix theorem apply. So when we look at this matrix, how can we think about the different statements of the invertible matrix theorem and how they can apply to tell us that this matrix may or may not be invertible? Well, let's think about statement D. So statement D says that the only solution of the equation Ax equals 0 is x equals 0. And if we notice, this matrix has a column of all zeros. So how could we use that column of all zeros to our advantage to try to find a non-zero solution to the equation Ax equals 0? Well, if you think about it, we might come up with a solution like the vector x equals 0, 0, 1. If we multiply this matrix by the vector 0, 0, 1, remember that a matrix times a vector represents a linear combination of the columns of the matrix. So multiplying by 0, 0, 1 would give us 0 times the first column, plus 0 times the second column, plus 1 times the third column, which would equal the 0 vector. But since x is not 0, this is a non-zero solution of the equation Ax equals 0, and so statement D is false. By the invertible matrix theorem, all 12 of those statements are false, and then in particular that means that our matrix is not invertible. Now that's sufficient to tell us that this matrix is not invertible, but let's practice using some of the other statements in our invertible matrix theorem. For example, what about statement E? So statement E says that the columns of this matrix are linearly independent. And again, we might notice that column of zeros, and we might also remember some of the characterizations of linearly independent sets from lecture 16, and that one of those characterizations tells us that if our set of vectors contains the zero vector, then the set must be linearly dependent. So since our set of column vectors does contain the zero vector, that means that the columns are not linearly independent, which means statement E is false, and then again by the invertible matrix theorem, that means that our matrix is not invertible. Let's try one more of our statements on this same matrix. What about statement F? Statement F says that the linear transformation T of x equals AX is 1-to-1. Let's remember what 1-to-1 means. We talked about 1-to-1 linear transformations back in lecture 20, and one of the things that we said about 1-to-1 transformations is that different inputs give us different outputs. That means that if we plug two different vectors into this transformation, we should get two different results. Or in other words, that we never plug two different vectors into this function and get the same result twice. So if we want to show that this transformation is not 1-to-1, what we need to come up with are two different input vectors that give us the same output vector. And again, we're going to take advantage of that column of zeros. And one of the things that we could do is realize that if we plug in 0, 0, 1, we already know that that's going to give us the zero vector by what we did before with statement D. We could also have plugged in 0, 0, 2, that's also going to give us the zero vector. But that's two different vectors that we plugged in that gave us the same result. That shows that our transformation is not 1-to-1, which means that, again, by the invertible matrix theorem, that our matrix is not invertible. Okay, let's move on to another matrix. But again, we're applying the same ideas and trying to use a wide variety of these different statements of the invertible matrix theorem just to see how they could apply to any given matrix. So here we see that we have a row of zeros. So how could we use that to our advantage to figure out how we could say that this matrix may not be invertible? Well, let's think about statement G. Statement G says that the equation AX equals B has a solution for all B in Rn, which is R3 in this case. So remember that A times X is a linear combination of the columns of this matrix. So we want to think about whether any possible vector in R3 could be produced by constructing a linear combination of the columns of this matrix. But because we have that row of zeros, any linear combination of the columns of this matrix must necessarily have a zero in its third entry. So any vector that doesn't have a zero in its third entry, like the vector 0, 0, 1, for example, will not be able to be produced as a linear combination of the columns of A. And so that means that the equation AX equals 0, 0, 1 has no solution. There's no way that you can multiply A times any vector to produce the vector 0, 0, 1. And so that means that by the invertible matrix theorem, our matrix A is not invertible. A similar argument could also be used to show that the transformation T of x equals AX is not onto, using statement I of our theorem. So similarly, because the equation T of x equals 0, 0, 1 has no solutions, that means that this transformation is not onto. Remember again, we talked about onto back in lecture 20. Onto means that for every vector b in the codomain, the equation T of x equals b has a solution. But if we let that vector b be the vector 0, 0, 1, then the equation T of x equals 0, 0, 1 will have no solution. That means this transformation is not onto, which means by the invertible matrix theorem, our matrix is not invertible. Let's look at one more matrix. So here, this one's a little bit more subtle. We don't have a row or column of zeros, but what you might notice is that the third and fourth row here have a relationship. We notice that every entry of the fourth row is equal to 2 times the entry in the third row. And that means that every linear combination of the columns of this matrix will still maintain that property. No matter what we multiply each column by, when we add all the results together, that fourth entry will still equal 2 times that third entry. And since every linear combination of A looks like that, but not every vector looks like that, all we have to do is come up with a vector that doesn't have that property. So for example, we could look at the vector 0, 0, 5, 6. In that vector, the fourth entry, 6, is not equal to 2 times the third entry. 6 is not equal to 2 times 5. And so that means that the equation AX equals B has no solutions, which means that using statement G, this matrix is not invertible. That's not the only way to do this. And again, I've just shown you a variety of different ways to apply the invertible matrix theorem, just to give you some ideas that you can try on your own when you start looking at your own matrices. So look for patterns, look for similarities among the rows and or columns, and think about which statement of the theorem could apply. There may be multiple statements that work. All you need to do is find one statement that you can definitively show is either true or false, and then all of the statements will be either true or false in that case. If all else fails, if you can't see anything that works for the matrix, then you can always fall back to row reduction to figure out whether the row-reduced echelon form of your matrix is IN. Thanks for watching this video lecture. You can find links to the other videos in this series and to the written textbook in the description below. If you're an instructor, you can contact me for more information about the over 300 online linear algebra homework problems that I've created for the free My Open Math platform.